Good day, everyone. Welcome to Ojibra Academy YouTube channel. And this time, we'll be looking at the concept of hybridization in organic compounds. When we talk about hybridization, that means we're talking about how covalent bonds, most importantly, are formed in organic compounds. And covalent bond, as we have it, is when two or more atoms they share paired number of electrons to bond together. That is what covalent bond means. And the type of bond that exists in all organic compounds is covalent bond. So it is just important for us to look at how the covalent bonds in organic compound are formed due to hybridization. Now, another thing we have to take note is that organic compounds are compounds that contain carbon atoms, hydrogen, and some other elements, as the case may be. So basically, there is no organic compound that can stand without carbon and hydrogen. Even if they can stand without hydrogen, they can't stand without carbon. So that is why it is important for us to check the hybridization of carbon atoms itself before we look at how other atoms are bonded to it. Now, for carbon atoms, carbon, the atomic number of carbon is 6. And we can write the electron configuration in two ways. Number one, we can write as 2, 4, and we can also write as 1s2, 2s2, and 2p2. 1s2, 2s2, and 2p2. Now, we're going to be using we'll be using the second configuration to check for how carbon hybridize or how covalent bonds are formed around carbon. Let us not forget that carbon is tetravalent in nature. In all organic compounds, carbon is tetravalent. What does it mean? This means it is surrounded by 4 bonds. Now, looking at this particular hybridization, let us look at it in um, a more explanatory way. Let's say we have 1s2 like this in a box. 1s2 means it contains 2 electrons. 1s2, the first and the second electron. 2s2, the first and the second electron. 2p, p orbital contains 3 boxes. So we have the first one, second one, and the third one, because the maximum number of electrons that p orbital can accommodate is 6. S can accommodate 2, p accommodates 6, d orbital accommodates 10, while f orbital accommodates 12. Sorry, 14 rather. So we have like different of 4 4 between the atomic orbitals. Now, so for 6, it is 2, sorry, for p rather, it is 2p2. So according to Hund's rule of maximum multiplicity, that electron filling into orbital singly before they pair up. So we have the first electron, the second one. We only have 2 electrons in p, so the third orbital remains empty. So for the sake of recognition, we can just label the p boxes as x, y, and z, so that we'll be able to know the one that contains electrons and the one that does not contain electrons. This particular type of configuration is what we call the ground state of carbon. The ground state of carbon, because it is assumed that at this ground state, hybridization has not occurred. Hybridization has not occurred in carbon at all. Now, what is even hybridization itself? Hybridization is the mixing or the blending of 2 or more orbitals to form hybrid orbitals. The blending or mixing of 2 or more orbitals to form hybrid orbitals. Now, let us now check when hybridization occurs in carbon, because at this particular level, hybridization has not occurred at all. So let's check when hybridization occurs in carbon. So we're going to have another configuration, because this time around, we want to blend and mix orbitals together to form hybrid orbitals. But the orbitals we are blending together, they must be orbitals of the same energy level or that has the same principal quantum number. The same energy level or when they have the same principal quantum number. Now let's take 1s2, 2s2, and 2p2. These numbers that are coefficient of these letters are what we refer to as principal quantum number. So it means for this first one, we can say it is in energy level 1, so to say. This second is at the energy level 2, while the third orbital is at also energy level 2 because they both contain 2. That means in carbon atom, hybridization can only occur between 2s2 and 2p2. 1s2 is at a lower energy level, so it cannot be hybridized with others. So let us now hybridize the two that are in the same energy level. So we're going to have something like this. For 1s2. Now, for 2s2 and 2p2 together, this is 2s2. Let me draw it here first before we bring it back to this place because I want to explain something. This is 2p2, x, y, and z, when hybridization has not occurred. Now, I want to hybridize them. It's like we are bringing the two orbitals together. So we are going to have a total number of 4 boxes because we are bringing 2s2 together with the 3p's. And in the two separate orbitals, we have 2 electrons here. All together here, we also have 2 electrons, making a total of 4 electrons. A total of 4 electrons in the two orbitals. This is orbital of 2s2, and these are the orbital of 2p2. Even if it is 3, they all belong to 2p2. So let us bring them together. I want to hybridize together now. So we're going to have the 4 boxes together. 1, 2, 3, and 4. We have 4 boxes now. I want to fill it with 4 electrons. Don't forget that they look like they are at the same energy level, like they are together now. They are no longer separate. That's the way it looks because we are hybridizing, we are mixing, and we are blending them together. So the 4 electrons now, according to Ohm's rule, like I said earlier, they are going to go into the boxes singly before they pair up. So we're going to have 1, 2, 3, and 4. 1, 2, 3, and 4. So the new configuration that we now have is 2s1 and 2p3. This x, this is y, and this is z. So the difference between the ground state of carbon configuration and the excited state, because this particular state is called excited state of carbon. Excited state or excited configuration of carbon. Now, it looks like we have transferred 1 electron from 2s2 to 2pz because this is 2px, this is 2py, and this is 2pz. So it's like we have transferred 1 electron from 2s2 to 2pz. Now we have a new configuration. And in this configuration, this is the configuration that explains the tetravalent nature of carbon because these orbitals, they are unpaired. They contain 1 electrons each. It means they are not paired, they are unpaired. So it means they still have a space to accommodate 1 electron each. And that is as a result of the tetravalency nature of carbon. That is what results to the tetravalency nature of what? Of carbon. Because it can accommodate 1 bond here, another bond in the second one, another bond in the third one, another bond in the fourth one. That makes carbon to be able to have 4 bonds around itself. Now, we have explained the concept of hybridization in carbon, how we come about this. And don't forget that we have 3 types of hybridization in organic compound. We have sp, we have sp2, and we have the last one, which is sp3. The sp, the sp2, and the sp3. Now we're going to take these types of hybridization one after the other. Let us look at what is going on there. I'm going to start with sp3. sp3. Starting with sp3, looking at the name sp3, it is telling us that we have one electron of 2s. You can see one s, p3, three different p's, one s and 3p coming together. So one electron of 2s plus or mixed with three electrons of 2p. So these 2 and 2 must reflect in our definition, because we have already said earlier that when hybridization occurs, it only occurs between atoms of the same principal quantum number. So that's why I said one electron of 2s plus 3 electrons of 2p to produce four new hybrid orbitals, that contains sp3 sigma bonds. Now, before I go further, let me quickly go to somewhere. Now, for covalent bonds are of two types. The first type is what we call the sigma bond, and the second type is what we call the pi bond. The sigma bond and the pi bond, those are the two types of covalent bonds that we have. Sigma, let me just explain in such a way that everybody will get the idea simply. For sigma, it shows that, or what formed sigma, let me put it that way. What forms sigma is hybridized orbital. Hybridized orbitals forms sigma. Why pi bond is formed by unhybridized orbitals. Unhybridized orbitals formed pi. So it means during hybridization, we will have some orbitals that come together, that are hybridized together. Like as in the case of the excited state of carbon, you discover that we have 4 orbitals that are hybridized together. Now I'm going to draw the diagram again so that we have a picture of what I'm trying to say. So for the first, this I drew for carbon, we have something like this. You didn't forget. 1 electron. This is X, this is Y, and this is Z. This is 1s2. This is not part of the hybridization at all. We cannot regard to this as unhybridized, no, because it's not even part of the hybridization in the first place. So this is not part of what we are looking at, because it is in lower energy level. Hybridization only concerns 2s1, this first one, and 2p3, the 3 electrons in p. That is where we have hybridization. So let's remove this completely, because we are not even considering it, so that we will not get confused. So let us focus our attention on this. Now, it looks like we have 1 electron of 2s, you can see, and 3 electrons of 2p coming together to form, this is a typical diagram of sp3 hybridization, because we have 1s and 3p. And what I was talking about the other time, that sigma bonds are formed due to hybridized orbital. Why pi bonds are formed due to unhybridized orbital? It means all the electrons, all the bonds formed in sp3, they will all be sigma, because all the orbitals are participating in the hybridization. So it means this one forms sigma bond, this one also forms sigma, the same thing with this, another sigma, and the same thing with this, another sigma. That is why we have four new hybrid orbitals that contains sp3 sigma bonds. It shows that in sp3, number one thing is that no pi bond. Number two, they have 4 sigma bonds. 4 sigma bonds, and no pi bond is a characteristic of sp3 hybridization. So in the next video, I'll be explaining sp2 and sp. So don't forget to like, comment, and subscribe to my channel. Thank you very much. Bye bye.